Okay, in the previous lesson we have talked about the importance sampling. Okay, just like this one, and so we can estimate the integral value for a given some coefficients that we calculated from the random samples. But in this case we will extend this feature into the sequential one. Sequential importance. I'm sorry. Importance sampling. SIS. And so, in this case, SIS extends importance sampling to sequential data. Suitable for dynamic systems where new data arrive over time. Okay, and so the key equations are given with the with this form. Weight updates can be initialized or calculated with this formula. WK I is equals to WK minus 1 I times, right now we need to utilize to the watt to our Bayesian estimator, just like this one. P YK XK I times P XK, the presence of the K I, and also we have a special function Q, just like the previous example. XK I, I'm sorry, for a given watt, XK minus 1 I and YK. Okay, this is simple, but how we can fill this equation in here? First of all, we need to give the watt this topic. Example of this one: estimate the state of nonlinear system. Just like this one, the state equation xk is equals to the xk minus 1 times 1 divided by 2 plus 25 xk minus 1 divided by 1 plus xk minus 1 square plus 8 cosinus 1 dot 2 times k plus v k minus 1. This is the Gaussian noise. And also we need to proceed with the observation with the watt yk is equals to xk over square 20 plus wk. Wk is also Gaussian noises. Okay, so we have two equations which is nonlinear form, and so we want to estimate to the watt the nonlinear dynamics of system or state, right? So how we can do that? For the solution, we need to firstly initialize some parameters. For example, the sample initial particles like x0 I from px0, the presence observation or the probability rate of these terms. And after that, we need to set the initial weights. W0 I is equals to 1 divided by n. Okay? This is the initialization. We set all the initial coefficients into the 1 divided by n. After that, we need to build to the to prediction and update state for each time step. Okay. The prediction is to the sample xki from p xk minus 1 I. Okay, and so the update rule is given with compute weights wki is equals to the wk minus 1 I times p yk xk I. Okay, these are the posterior probability for the for R conditions, and also this one xk, the sampling from the random point in here, just like this one. And also we need to to normalize weights to sum of all of them is equals to the 1. This is the normalization process. Okay, and so continuously we build to recursively. Updating these particles and weights, we will get state of nonlinear system. Okay, this is how we can build a particle filter basis in here. Okay, but firstly, we may have a problem in here about the sampling, because the sampling or the particles may generate or with some unwanted conditions in here, because it's totally random values. But always we update the coefficient. But how we can prevent these situations in here? And so the resampling technique may be used in here. Resampling techniques. So in this, the particle degeneracy can occur or happen in the system, where after several iterations most particle or random points have negligible or unimportant weights. For example, if we have the 5 weights and so 4 of them is small and then 1 weight always win, and so we go to this direction, and resampling addresses this issue. By focusing a particle with higher weights. Okay, most important particle is equals to what? Higher weights. And so the resampling is applied on these higher weights to normalize or to get what the mean values of these terms. And so we can achieve to what the most important part of the path, or we can normalize all the coefficients based on this information. Okay? Because at the one direction, for example, if we have the 4 particles weights, and so these weights are so small that one of them is greater, for example 0.9, and so we always going to this sample, and so this 0.9 should be normalized or resampled in order to what? In order to create the effects of the new particles. Okay. So how we can do that? Firstly, in order to do that, we need to give the new concepts the effective sample size, ESS. Okay, and so EFF is equals to what? 1 divided by N. I is equals to the 1, and so VKI square. Okay, and then we can apply by using this term systematic resampling. Okay, because it's the norm values of these terms, and then this effective sample size can be determined by using these terms. Okay, and so if we have the 10 samples, for example, one of the higher weights is to what is more bigger than the other ones, and after that we apply this rule, and then we resampled everything in here. For example, how we can apply it? The example can be given in here. Given particles with weights perform systematic resampling. Why is systematic? We have the equation, just that simple. Or we can resample the system based on the what? Based on the random sampling. First of all, we need to compute cumulative sum of weights. Ci is equals to what? Ji to I, J1 up to I, Vkj. Okay, this is the first equation that we needed to apply. This is I. Okay, this is 1, and then we should generate random number. U1, it's a uniform distribution, should be used 0 and 1 divided by n. This is the standard deviation, the variance values of these terms. And also we need to compute points. Ui is equals to u1 plus I minus 1 n. Okay, this is the resampling settings. And so if we have these terms, and so we can resample the particles for each ui, which is the generated random number, find j such that Cj minus 1 ui smaller than this one and ui smaller than Cj, and select particle xkj. Okay, and so this gives us to what? Computationally improves results to focus on more probable particles. Okay, that's all. And so in the next lesson we will drive the particle filter algorithm based on these 4 topics. Okay.